Okay, we're off. Good afternoon, students. Now, it's Friday the 27th of March, and the last time that we met as a class was actually exactly 2 weeks ago on Friday the 13th of March. And that's a long time ago. So what I want to do is to give you some thing to keep things ticking over with your double award science. So give you a little bit of science to do, a science lesson to do at home. For this lesson, you are going to need this booklet. This is your white notes, which we all have. Now, the good news is that everybody's got one. The bad news is that this doesn't cover the whole of P1. This is only part 1 of it, I think. And you have got to get the second bit to do the second half. But I don't know how we're going to do that. But we do have all of forces in this booklet, so you can use this to do that. The other bad news is that this is not the greatest booklet. I'm not liking it very much, and that's why we didn't use it very much in motion. But we are going to use it for the forces topic because it's what we've got. Now, my computer's giving me a little bit of bother here, so I haven't got the second camera on. That's why you can't see me. And I've reduced the resolution a bit as well so it can keep up. Now, we're just going to do this and see if we can get it to work. Okay. All right. You'll need your white notes for this, as I've said. If you haven't got them, I'd suggest you pause the video at this point and go get them. When you're back, I'm going to give you the learning objectives for this lesson. Here we go. What we are learning in this lesson is, what is Newton's first law? Okay. And the success criteria. What you will do in order to complete this lesson is you will brainstorm what we already know about forces. We will draw some easy force diagrams. We will state Newton's first law in words. And then we'll use Newton's first law to explain what happens to objects when forces are balanced. The reference for this then is your white notes. That's that. It's Physics 1 and it's page 29 onwards. So in yours, you should go to page 20, did I say 21? 29. Page 29, which is here. There it is, page, you just see at the bottom there, there's page 29. Now, I've actually already written on mine, so I've printed out the relevant pages. This is your page 29. So this is topic 2 and it's forces. Now, forces can be of different types. You might remember in our last lesson we did brainstorm a little bit about what we knew already about forces, the different types of forces and situations in which they act. So, for example, we have the elastic forces. So forces can be the force of tension in an elastic band. Okay. The force of gravity that makes objects fall. The force of friction. So when you push something, the force of friction acts to stop you pushing it. We have the force of buoyancy, the upthrust that you feel when you're floating in water, and so on and so forth. Okay. Now, if we turn over, page 30 is formulas, keywords and definitions. There's a space there to write in Newton's first law and his second law and some keywords. You can fill that in a bit later on when we've got through the unit a bit, and you can use that as basically a summary. Page 29, 30. This will be your page 31 then. Okay. So you might remember about ideas you have about forces and what they can do. Okay. There's a little mind map there, but we'll fill in the gaps first and then we can come back to the mind map. Now you might remember that in our first lesson on forces 2 weeks ago, we went outside and we did 2 things. We did the giant catapult, using the giant catapult to shoot water balloons across the pitch. So that was using, well, I suppose the force of an elastic band, the tension in an elastic band, a giant elastic band, to launch the water balloons up, and the force of gravity which brought them back down again. We also did the water rocket. Remember it? You pump it up and the pressure of compressed air trapped inside the bottle forces the water out. That produces a force and that shoots the rocket up into the air. Okay, now out of all of that we get the following. Let me zoom in a little bit. So a force can either be one thing or another. Do you remember what those things are? Have a little think. A push or a pull. Okay, so we can define a force as either being a push or a pull. What can a force do? It can cause a body at rest to start moving, to move. Or if the body is already moving, it can change its speed or its direction of motion. And it can also change the shape of an object. So think of a football. If a football is just sitting at rest on the pitch, if you exert a force on it, a push, by kicking it, for example, then that will cause it to move. Once the football is already moving, if it's rolling across the pitch, if somebody else then kicks it and exerts a push on it, that can change its speed. You can just kick it in the direction that it's already moving, in which case it will speed up, so you change its speed, or you could kick it off in a different direction. And actually, when you kick a football, that does change its shape a little bit. The football squashes a little bit as it's kicked and then bounces back. Okay, now we can take that a step further and we can say some forces cause an object to speed up, and you remember that the word for speed up is accelerate. Oh, by the way, if you haven't already guessed, the idea is that you fill in your own notes as we go along. Others cause it to do the opposite of speeding up, which is slowing down. Do you remember what slowing down is? Decelerate. If the force causes the object to decelerate, it is called a, well, you could call it a decelerating force, or in enniskillen they like to call it a retarding force. So retardation just means the same as deceleration. It means slowing down. Now, the reason a cyclist, singular, wears tight clothes, so a cyclist wears a lycra cycling kit, is to reduce air resistance, which is just the frictional force between the air and the person, also known as drag. So air resistance is one resistive force and there are others. Now, yes, we got all of that. Okay, let's go back up to the brainstorm. Right, so types of forces. Well, a force is a push or a pull, and we've already seen some types of forces. We've seen the force of gravity, and the force of gravity in an object is also known as its weight. We've mentioned the force of friction. We've mentioned elastic forces, the force of a stretched rubber band or piece of elastic. And what else did we mention? Gravity, friction, elastic force. Can't remember. Might have been another one. The units of force, you might remember, are newtons. Okay. The symbol for newtons is big N. And to give you an idea of how big a newton is, 1 newton is the amount of force that gravity exerts on an apple. So it is the weight of an average sized apple. So if you hold an apple in your hand, the force that you feel is more or less 1 newton. Okay, effects of forces. Well, they can make things start moving or stop moving. If a thing is already moving, they can make it speed up, which is to say it will accelerate. They can also make an object, whoops, I was going to say speed down, I mean slow down, which is to say decelerate. And they can also cause an object's motion to change direction. And the last one, which we could squeeze in over here, is a force may not change the motion of an object at all, but it might change its shape. Okay, I think that's enough of that. By the way, in this lesson I don't want to go over about, certainly don't want to go over 30 minutes. Okay, now the next thing is force diagrams. So we can represent forces in diagrams using arrows. Okay, a force has both a size, which is just how big it is, how many newtons it is. It also has a direction. Now, that next bit, for our purposes, we're going to leave that bit out. The size of a force is measured in units of newtons, as we've just said, and the symbol for newtons is capital N. When drawing forces, if we want to draw a force in a diagram, it's usual to represent the direction of the force by an arrow and the size of the force by the size of the arrow. So, for example, here we've got diagrams of 2 people, and we can draw forces to represent, or arrows on the diagram to represent the forces acting on the people. So it says, draw on a labeled force arrow representative of the weight of these 2 people. One of the persons weighs 600 newtons while the other weighs 1200 newtons. Can you work out which is which? Okay, the person on the right is the 600 newton person. Now his center of gravity is round about in his middle, so we can draw an arrow to represent his weight, and the arrow represents his weight. We could use W to stand for weight, and the size of the weight is 600 newtons, so capital N for newtons. And the arrow points downwards because weight acts downwards. Now the other person, their center of gravity is also about there, and their weight also acts down. Now, we can make the arrow twice as long, because this person weighs 1200 newtons, which is twice 600, so it's twice as big. So their weight is 1200 newtons. Okay, we don't need to be too fussy about the size of the arrow, but we do need to be fairly fussy about the direction. Now, let's try a slightly more complicated example, which is a car. I'm just going to focus again, see if that's as focused as it can be. I think it is. Okay, so here's a car, which is supposed to be going along a road. Now this car actually appears to be floating above the road, which isn't great. So let's bring the road to meet the car. There's the road. Okay, now what forces have we got here? The engine of the car exerts a thrust of 10,000 newtons. And this is matched by 10,000 newtons of drag. The car has a weight of 6,500 newtons matched by a 6,500 newton reaction from the ground. Draw the force arrows for the 4 forces on the car. Actually, I'm going to draw... we'll draw 4. Okay. Now the centre of gravity of the car is somewhere around its middle. Let's pick up the forces in turn. A thrust of 10,000 newtons. Well, thrust means the forward force that drives the car forward. In other words, the driving force produced by the engine. So to draw that, we need an arrow that goes forwards. Okay. And we'll label it. It's thrust. And it's 10,000 newtons. Okay. Now, this is matched by 10,000 newtons of drag. Well, drag is the frictional force, the resistive force of air resistance, and it acts to oppose the motion of the car. In other words, it acts backwards. If we want, no, we don't do that. Like that. Now, those 2 arrows should be the same length, at least roughly the same length, because the drag force matches the thrust in this case. Okay. So we've got an arrow pointing forward for 10,000 newtons of thrust. We've got an arrow pointing backwards, which represents the 10,000 newtons of drag that's holding the car back. Okay, I can't resist it. We'll draw some drag lines. Okay, the car has a weight of 6,500 newtons. Well, weight is the force of gravity, and gravity acts down. So we draw a downwards arrow to represent the weight of the car. And the value of the weight is 6,500 newtons, like so. The weight is also matched by a 6,500 newton reaction from the ground. Now, if you remembered, we talked a bit about reactions, I think. So, the car is resting on the ground. Now, if the car was not resting on the ground, its weight would pull it down and it would fall. But it is resting on the ground, and therefore the ground stops it from falling by pushing up on it. And the force of the ground pushing up on the car we call the reaction force. Now, the car is actually in contact with the ground here and here, at the front wheels and at the back wheels. In fact, it's in contact with the ground at 4 points, where each of the 4 wheels meet the road. So actually the reaction forces act up through the wheels here and here. But to make it simpler, we're going to represent the reaction force due to the ground pushing up as a single force with a single force arrow. So it's not really terribly realistic. The reaction force of the ground is actually the force of the ground pushing up at each of the wheels, but we'll represent it by one single reaction force. And we're told, well, the reaction must balance the weight. If it didn't, the car would sink down into the ground. So the total reaction at the 4 wheels is 6,500 newtons pushing up, like that. Okay, now, if the car is moving along the road, let's assume that it is because there's a thrust force, what can you say about the motion of the car? Now, if you need to, pause for a moment and have a think about it. The car is moving along the road. The engine is pushing it forward with 10,000 newtons. but the drag force is holding it back with a force of 10,000 newtons. So what's it going to do? Is it going to speed up? Is it going to slow down? Is it going to stop? Well, actually it's going to do none of those. It's already moving. So say it's moving along at, let's say, 60 miles an hour. The forward force is matched by the backward force. So overall, those forces are balanced. So there is no leftover force to make it go any faster, nor is there any leftover backward force to make it go any slower. So actually the thrust and the drag cancel each other out. So it neither accelerates nor decelerates. It keeps going at the same speed and in the same direction. So what we can say is that it keeps moving at the same speed and in the same direction. Okay, now we're over 20 minutes and I said we wouldn't exceed 30, so we need to crack on here. Hope you've got all of that. And we'll turn over. So this will be your page, well, your next page. I think we're on 33 now, 31, 32, I think this is 33 for you. Okay. Now, we now meet Newton's first law. Okay. And this is what Newton's first law says. It says, a body stays at rest or continues to move in a straight line with a constant speed or uniform velocity unless an unbalanced force makes it behave differently, that is, to change its speed or direction. Okay, now that's important, and actually you need to learn it, so I'm going to highlight it. Now actually your specification requires that you know this first law and can recall it. So therefore we need to learn it. So we'll put a little note beside it. You've got to learn that by heart. A body stays at rest or continues to move in a straight line with a constant speed unless an unbalanced force makes it behave differently, that is, to change speed or direction. Now, Newton's first law, we could say, is the law of balanced forces. It's all about what happens when forces are balanced. Okay. Now, let's see if we can say what it means. Really, there's two cases being described here. There's what happens if a body stays at rest, and what happens if a body is moving. Okay. Now, to explain this, let's look at an example. Okay. So, here's an object. Can I show you this? I think I can. Right. Here's an object. It's a bottle. And yes, I did drink the contents. Okay. If we just set the bottle on the table, like this, you can see that the bottle is at rest. It's not moving. Now, what can we say about the forces acting on it? Well, there are two forces. There's the bottle's weight, which is pulling it down towards the table, and but the table pushes back on the bottle with a reaction force, and the reaction force is just big enough to balance the weight. So therefore, the forces on the bottle are balanced. Now, what does the bottle do? Well, it doesn't do anything. It's at rest, and it stays at rest because the forces on it are balanced. it'll only move if an unbalanced force comes along and makes it move. Okay, so the bottle is at rest and it remains at rest because the forces on it are balanced. Okay, now there's another thing we can do with the bottle, which is if I turn it onto its side like this and then give it a little push to get it moving and then let go. It does that. Let's do that again. Okay, now you might remember we did this in the lab but with an aluminium cylinder. So when it's moving, because it's on its curved side, it doesn't feel very much friction. So therefore, at least over a short distance, we can ignore the friction. There's almost no friction. So there's no friction to hold it back. Now likewise, it's not a car, it doesn't have an engine, so there isn't any forward force, there's no driving force to make it go any faster. But once it's moving, there's no forward force, and there's no backward force, there's no friction force either. So therefore, we can say that there's no force acting on it. The forces forward and the forces backwards are balanced. And therefore, what does it do? Well, it keeps doing what it was already doing, which is rolling. So it keeps moving. It keeps moving at the same speed and in the same direction. Now, if you don't believe me, go get your own bottle and try it. Okay. So, let's see if we can turn that into science language. Right. So, if two forces are equal in size and opposite in direction, then the forces are said to be balanced. Balanced forces will not change the speed or direction of an object. If, that should be, an object is stationary, it will remain stationary. Remember that stationary is just another word for at rest. If the forces are balanced. Okay, so forces that are equal and opposite are said to be balanced. Balanced forces will not change the speed or direction of an object. So the first case is if an object is stationary. So that's the bottle standing on its base. Then the bottle standing on its base is stationary, and it remains stationary if the forces are balanced. And in the case of the bottle, they are. The weight and the reaction match each other. Okay, but what if an object is not at rest, but is moving? So here's a car moving at 60 kilometers per hour. Now, if the thrust equals the drag, now we know that the thrust equals the drag because the arrows are the same size, but we could put numbers on them. Suppose the thrust is 1,000 newtons, and the drag is also 1,000 newtons. That means that the forces are balanced. The thrust equals the drag, but they're in opposite directions. The forces are balanced, the car is moving, so it will not accelerate, it will not decelerate, and it will not change direction. It will keep moving at a constant speed. Okay. Not only that, it will keep moving at a constant speed in the same direction. So this is like the bottle. When the bottle is rolling across the table, it's moving, it's got a speed, but the thrust and the drag are balanced. In fact, they're both zero. There is no thrust, but there is no drag. So the forces are zero in both directions, they're balanced, and so the bottle doesn't accelerate, doesn't decelerate either, and it doesn't change direction. It just keeps moving at a constant speed and in the same direction. Okay, we've just gone over 30 minutes, but we'll finish off the last example. A fighter plane. So here's a fighter plane. It's moving at 200 kilometers per hour in level flight. And if its engines are producing a thrust of 1 million newtons forward, but the drag force of the air on it is also 1 million newtons, what will it do? Well, it will continue flying at a constant speed. And in the same direction. Why? Because the thrust force forward equals the drag force backwards, and therefore the forces are balanced. And in this case, the forces are balanced, so the fighter plane is already moving, so it will keep moving at the same speed and in the same direction. So it continues flying at a constant speed, and we should add in the same direction. Now you might say, what happened to the weight? The fighter plane still has weight, but that's balanced by the lift force of the wings. We've left those forces out of here in this case because it makes things a bit simpler. Okay, so when forces are balanced, an object will either stay at rest, like the bottle, or if the object is already moving, it will continue to move with constant, they're going to say velocity, but we're going to say speed. Continue to move with constant speed in the same direction. Okay. And if we go back to Newton's law says a body stays at rest unless an unbalanced force makes it behave differently. Okay, in other words, a body stays at rest if the forces on it are balanced. A body continues to move in a straight line with constant speed unless an unbalanced force makes it behave differently. In other words, an object will continue to move in a straight line with constant speed if forces are balanced. So that's what Newton's first law is saying. It's saying that if the forces on an object are balanced, then if it's at rest, it stays at rest. If it's moving, it will keep moving at a constant speed and in the same direction. So the wording's a little awkward, but when you apply it to examples like this, it's kind of just common sense what objects do. All right, I'm going to stop at that point. If you filled in all your notes like that, that's pretty good. There are no exercises to do at this point, but we'll have another go at this in the next lesson and look at what happens in the case of unbalanced forces. Let us just go and do a quick review of our success criteria. Right, so we were to brainstorm what we already know about forces. Yes, we did that. We had a look at, I'm going to go back over. So we had a look at types of forces, forces of push or a pull. I'm going to go back over it. Okay, we looked at our first page, which we didn't fill in. Second page, didn't fill in yet. Third page, brainstorm of forces. Yes, did that. So we looked at force as a push or a pull, different types of force, the unit of force, and what forces can do. Okay. Did we draw some force diagrams? Yes, we did. So the idea that a force can be represented in a diagram by an arrow, and the arrow gives its size and its direction. Did we state Newton's first law? Yes, we did. There it is, stated and highlighted. And you need to know it by heart. And number 4, did we use the law to explain what happens? Well, yes. So we considered the example of the bottle just sitting on the table. We considered the bottle rolling along the table at a constant speed. And then we thought about the car and the fighter plane as well. Okay. That's all the physics we can take this afternoon. I hope you're enjoying lockdown and distance learning. And I hope you enjoyed learning with me this afternoon. I've enjoyed learning with you.